Welcome everybody to the next video in our series on probability and statistics. I am Dr. Lathram, and today we will be talking about the Gaussian family of distributions. So let's begin by looking at the convergence of the integral from minus infinity to infinity of e to the minus x squared. Now we know that for x greater than or equal to 1 that we have the inequality that x is going to be less than or equal to x squared. Now e to the negative x, as we're familiar with, is a decreasing function, and so as long as x is greater than or equal to 1, then x less than or equal to x squared implies that e to the negative x squared is going to be less than or equal to e to the negative x. So what we have then is the convergence of the integral from 1 to infinity of e to the negative x dx is we can evaluate that. That's e to the negative 1 and then minus the limit as b goes to infinity of e to the negative b. Well, e to the negative b is going to go to 0, and so the limit is just 1 over e, which is definitely less than infinity. And so by comparison, because e to the negative x squared is going to be less than or equal to e to the negative x, then the integral from 1 to infinity of e to the negative x squared dx is going to be less than or equal to the integral from 1 to infinity of e to the negative x dx. And so we have convergence of that portion. Now, e to the negative x squared is a continuous function, and it's a continuous function on a closed and bounded interval for 0 up to 1. So what that means is that the integral from 0 to 1 of e to the negative x squared dx is finite. So that's obviously not going to blow up. And because we have shown that both of the integrals are finite from 0 to 1 and then from 1 to infinity, both of those are finite, therefore the integral from 0 to infinity of e to the minus x squared dx is also finite. And it's symmetric around the origin, so just doing a simple substitution, we've got the integral from minus infinity to 0 of e to the negative x squared dx is also finite. And so one more time, because our integral from minus infinity to 0 and from 0 to infinity, because both of those integrals are finite, we add them together, we get another finite value, and that value is the integral from minus infinity to infinity of e to the minus x squared dx. And so, kind of using this kind of piecewise argument, we've shown that the integral of e to the minus x squared over the entire real line is going to be some finite value. But the real question then is, what does the integral actually equal? It's finite, but what is it? And so I'll make the claim that the integral from minus infinity to infinity of e to the negative x squared is the square root of pi. So let's see if we can prove that. So we know that it's finite. And so let's look at the double integral from over the entire real plane, so from minus infinity to infinity and minus infinity to infinity for x and y of e to the minus x squared plus y squared. Well, using our properties of exponentials, we can separate that out into e to the minus x squared times e to the minus y squared. And because those are the product of two functions, we can separate them out of our double integral. And so we have the integral from minus infinity to infinity of e to the minus x squared, and the integral from minus infinity to infinity of e to the minus y squared. Now those are, for all intents and purposes, the same integral, because our variable of integration really doesn't matter. And so integrating over the whole plane just gives us the square of the integral over the entire real line. Okay, so now we've related our integral over the entire plane to our integral over the real line, let's look at the integral over the entire plane again. So let's do a change of variables. Let's switch over to polar coordinates. So if we let x equal to r cosine theta, y equal to r sine theta, then if we're doing a multivariate change of coordinates, we need the Jacobian, which is just partial x, partial x, partial theta, over partial y, partial r, partial y, partial theta. We take the determinant of that matrix, remembering some of our trig identities, and so we see that the Jacobian is just r. So that our integral over the entire plane just becomes the integral from 0 to 2 pi and 0 to infinity of e to the minus r squared r dr d theta. So integrating with respect to r, now this is possible to do with just a u substitution. So what do we have? The integral of e to the minus r squared r dr becomes negative 1/2 e to the minus r squared from 0 to infinity. Well, that just is a value of 1/2, which leaves us with 1/2 times the integral from 0 to 2 pi of d theta, thereby just giving us a value of pi. And so what happens? Our integral over the entire real line, or the square of the integral over the entire real line, is equal to pi, so we can take the square root of both sides, and we see that the integral from minus infinity to infinity of e to the minus x squared is sure enough the square root of pi. And so this is the graph of our function e to the minus x squared. And so what we've determined is that the area underneath that curve is just the square root of pi. All right, so now the natural question is, we've evaluated this integral. We know that it's finite. We can normalize it to get a probability distribution out of this. But how do we go about getting an entire family of probability distributions out of this? Well, the answer is that we'll take the integral, but we'll do that with respect to a family of transformations, and these are going to be affine transformations. So if we do transformations of the form y equal to ax plus b, where a and b are real numbers and a is not 0, then our dy just becomes a dx, and x becomes y minus b over a. So if we substitute that into our integral, then we see that the square root of pi is going to be 1 over a times the integral from minus infinity to infinity of e to the minus quantity y minus b squared over a squared. And so if we just divide both sides by the square root of pi, we see that 1 is going to be equal to 1 over a times the square root of pi times our integral from minus infinity to infinity of e to the minus y minus b quantity squared over a squared. And so now by choosing different values for a and b, we've developed this parameterized family that are determined by these real numbers a and b. All right, so let's take a look at the moment generating function for one of these distributions. Well, the moment generating function is just going to be the expected value of e to the ty. So we throw that in there, and we get e to the ty times our PDF. But because they're exponentials, we can put them together so that we've got the integral over the entire real line of e to the minus y minus b quantity squared minus a squared ty, all of that over a squared. So if we look at that exponential, if we look at that power, it's really just a quadratic. And so we can complete the square on that thing. And if we do, we see that we have an expression that looks like this. So y minus b plus a squared over 2 times t, that quantity squared, and then our new constant becomes ta squared times the quantity of b plus a squared over 2t. So if we plug this expression back into our integral, then we are able to separate out this ta squared times b plus a squared over 2t. We can separate that out using our properties of exponentials again. And so if we go ahead and pull that to the outside, because it has absolutely no bearing whatsoever on y, then if we look at our expression on the inside, we see, hey, wait a minute, that looks like another one of our family of distributions, where we've just got this kind of new, strange, weird expression for b, and our a is still the same. And so because that's a member of our family, we know that this whole integral is just 1, and so what we're left with is e to the tb plus a squared t squared over 2. So that's going to be our moment generating function for one of these distributions. Well, if we take the derivative with respect to t, we get this expression. Then set t is equal to 0. What we find is our mean for that distribution just happens to be the value b. If we take the second derivative and plug in t is equal to 0, we get e to the y, the expected value of y squared is just b squared plus a squared. But that means that our variance, sigma squared, is just going to be a squared once we get that value out. And so typically what people will do is to, instead of using values like a and b, we'll just say that instead of using b, we're just going to call it mu for the mean of our distribution. Instead of using a, we're just going to call it, say that a squared is just going to be sigma squared. So we'll use the value of sigma squared. And what we've just done is to come up with a new family of distributions. Now, a random variable y is said to have a Gaussian distribution if and only if the density function of y can be written in this form. So we've got kind of this extra value of 2 in here. You'll kind of see why that shows up in a little while maybe. And so 1 over sigma times the square root of 2 pi e to the minus y minus mu quantity squared over 2 sigma squared is the PDF for our Gaussian family of distributions. And so we'll denote that with our parameters sigma being a positive real number and mu being any real number. Then we denote that y tilde y distributed by a normal distribution with a mean of mu and a variance of sigma squared. So then, based on what we've just done with the moment generating functions, we've pretty much proven this theorem that the expected value, so the mean of a normally distributed random variable, is just going to be mu, and the variance is going to be sigma squared. So again, that was really just falls right out of the moment generating function. Now, let's look at some theorems that kind of are going to be really useful whenever it comes to really applying the family of Gaussian distributions. So the first one is called the linear combination theorem. So what exactly is a linear combination? Well, you pick a bunch of real numbers, a sub 1, a sub 2, all the way up to a sub n. You've got a bunch of independent random variables, y sub 1, y sub 2, all the way up to y sub n. And a linear combination of those, you are just multiplying the first one by the first real number, second one by the second real number, third one by the third real number, all the way down to the nth real number times y sub n, and you add them all together. That is basically what we mean when we say that we have a linear combination of the y1 up to yn's. So if we have a new random variable x that is the linear combination of those, then this x also has a normal distribution with an expected value, which is a linear combination of the expected value for the y sub i's and a linear combination with the squares of our coefficients for the variances of our y sub i's. So let's see why that might be true. Okay, so falling back on something that we talked about in our video on moment generating functions, so if you need to go back and review that, please do. If we have a constant times our random variable, then how that impacts the moment generating function is that we take that scalar and we just move it inside to become a times t of our usual moment generating function. Now, if we look at the expected value of y, then that's going to be the expected value of all of that linear combination, so t times that linear combination. Well, if I distribute the t, and then using the properties of our exponentials, I can separate that out into this product. Now we use the fact that we have independence, and again, this is another property that we talked about back in our video on moment generating functions, that if a collection of random variables are independent, then the moment generating function of the sum of them is the product of the moment generating functions. And so the expected value of this product just becomes the product of the moment generating functions. Each one of the variables y sub I is normally distributed, so we know what the moment generating function looks like of that. So we have a product of exponentials. Again, using our properties of exponentials. When we have that product, we can make it a sum of the exponents. And so we add all of the exponents together. And now, because our moment generating functions uniquely determine the distribution, so this was the power, or one of the big properties that gives us a lot of power in the moment generating functions. The moment generating function determines the distribution. The distribution uniquely determines the moment generating function. And so they're kind of mirror images of one another. Once we know one, we know the other. And so what that means is, if we look at the form of the moment generating function that we had up here, that is the moment generating function of a normal distribution with a mean, which is the sum of the linear combination of the mu sub i's, and the variance being the squares of the variances of our y sub i's. And so, because the moment generating functions uniquely determine the distribution, we get our conclusion. So one immediate application of that, we have this corollary, is that if we have the difference of two independent normal variables. So if x is normally distributed with mu sub 1, with a mean of mu sub 1 and a variance of sigma sub 1 squared, and y is also normally distributed with a mean of mu sub 2 and a variance of sigma sub 2 squared, then because x and y are independent, if we look at the difference of x and y, that will also be normally distributed with a mean of mu sub 1 minus mu sub 2 and a variance of sigma sub 1 squared plus sigma sub 2 squared. Now this is going to come back to again be, and also as a second corollary to our linear combination theorem, if we have y sub 1, y sub 2 all the way up to y sub n, is a collection of IID. Now IID is going to be one of our shorthand notations for saying that a collection of variables are independent and identically distributed. So independent, identically distributed, IID random variables, with each one of them normally distributed with the same mean and the same variance. Then if we take the average of those variables, And then the average turns out to be normally distributed with a mean of mu and a variance of sigma squared over n. So what that really means, so where this particular theorem really comes into play, engineers will use this kind of thing, that if we're sending a particular signal across a wire or something, then usually the noise that gets sent along with that signal is also modeled as a normal distribution, kind of a normal error that we have. And one way of reducing that error is applying this theorem. So that if we take several samples of our signal, and we take those samples and we average them together, then if we think of our mu as being our true information, our true signal that we want to go through, and the variance as just being our error, our noise, then what this is telling us is that our noise will actually go down by a factor of 1 over n, whenever n is our value for averaging. So this theorem actually comes into play quite a bit and ends up being very useful in engineering and electrical engineering, signals research, that kind of thing. So this has been a real quick introduction to the Gaussian family of distributions. I hope you've gotten some good information out of this, and I will see you all next time.